All right, we'll get started. This is discussion 14, and we're going to talk about regression essentially. Before we get started, any questions? Any questions about the project? I've already created your projects, so you should have received a comment. The way we now envision is like if you received a comment and I've kind of taken, if I have had to take your points off on certain part, that's because we just want you to kind of do it again. So this will not serve as a penalty for your final project. Okay, so this, if you did not score like a full score, don't worry about it. All we want to do is make sure that the thing that you did not get it right, you improve upon that in your final project. Okay, so in most cases, I would have left a comment saying that what's wrong about it or how you should think about it differently. So just to give you an example, if you're doing ANOVA, uh, we talked about this last week that if you're doing ANOVA, you kind of implicitly require that you have in the categorical variable has three groups. Okay, because if you just have two levels, so for example, there are a lot of data sets where you're looking at sex, and if it's just male and female, which means there are just two groups, then I don't really need to do ANOVA because doing an ANOVA is essentially similar to doing a t-test in this case. But what we want to do is we want to essentially have do one-way ANOVA, and this is kind of uh, motivated by the fact that we want you to be able to understand how to do an ANOVA. Okay, and hence we require something which is slightly more involved, and that essentially happens in the form of presence of three levels. And when I say level, that means three, at least three groups is something that you can classify it based on your categorical variable. So that was one common observation that some of you ended up choosing a categorical variable which had just two levels, which meant just using two groups, which there's nothing wrong about it. First of all, the only thing is like you don't really need to do ANOVA on this. And if you do ANOVA and you do a t-test, you'll get exactly the same results. Okay, so it's analogous. Doing an t-test and an ANOVA on a categorical variable which just has two levels or two groups is going to give you identical results. Okay, so that was one observation. The other observation was on if you're doing ANOVA, we require implicitly that the data is normal. Okay, and when I talk about normality, the data in some sense has to be continuous. So if you're working with counts data, so if you only have integers, this assumption is generally not satisfied. Okay, one way to get around that is to transform this into some other variable. So I can take like something like a square root or take a log, and hopefully that will be normally distributed. But we do this in an advanced class. Okay, so the safest option for us right now, if we want to do an ANOVA, is to work with something that's continuous. Okay, so I've left a comment. If you're working with counts data, I'm not going to penalize you for that, but just make sure you understand that the best choice would be something that's actually continuous. Okay. All right. We get started. Okay. There's a question. Reading that. So for your data, there's only one useful categorical variable. Yeah, that's fine. So if you have the categorical variable which had four levels, so maybe I did not make it clear. So one categorical variable is okay because we are doing one-way ANOVA. This categorical variable needs to have four levels. When I say levels, that means uh, it's a category, and within this category, there are four groups. That's what I was talking about. Does that answer your question? Okay. Okay, so one way ANOVA, we need just one categorical variable. Now this one categorical variable needs to have at least three groups. Okay, so if you look at the different categories within this categorical variable, so I call these levels, you can call these groups. It needs to be at least three. So if you're looking at, let's say, sex, and if you just have male and female within sex, that's kind of not sufficient for doing an ANOVA. Okay, you can just do a t-test. But if you have, I think there's one data set where you have a male, female, and infant. Okay, so if you have three, you're good. So you don't have to worry about anything. Okay. Any other questions about the project? Okay, so it's due on April 28th, and I would strongly encourage you that you use the template. So if you go on Blackboard, above the project one link, you have a link to the PDF and the RMD, the R Markdown notebook, which you can download and use that to turn in your second part. The reason I designed it was because it kind of lays down these a structure, which if you follow, you'll actually have, it'll be very easy for you to actually follow and answer each and every question. Okay. Okay. Any other questions about the project? Okay. In that case, I'm going to start working on discussion 14. I'm going to stop my video. All right. So we essentially start off with a problem on discussion, on correlation. And it's a very simple problem. You're given a scatter plot. And this is actually taken from one of the data sets that already exists in R. On the x-axis, you see the horsepower. On the y-axis is your q-sec, which is essentially the time it takes to speed up to 1/4 of a mile. Okay. And what we are asked is, we are asked, from the scatter plot, do you expect the correlation coefficient to be positive or negative? Okay. And the answer is very simple, right? So you see a kind of a linear trend. So if I were to randomly look at this trend, then this would look like something like this. Okay. And essentially that means that I expect this to have a negative correlation. Okay, let me use this space here. I expect this to have a negative correlation. Okay. So what essentially is correlation capturing? So correlation essentially is capturing what is correlation. So we use a different color because, okay. So correlation essentially captures the relation between, captures the relationship between two variables. Okay, and these variables are numeric, x and y. So given two variables, I want to be able to capture, can I use information that exists in x to predict what y value should be? Okay. So this value correlation, which is r is a value between 1 and -1. Okay. The higher the value of r is, more predictable is y from x, and vice versa. Okay. So correlation does not depend on, so correlation of x and y is equal to correlation of y and x. Okay. And the only information in some sense that you need to be able to calculate this correlation is this value. So your R is given by, so you're looking at, in some sense, you're looking at how much amount of deviance do I see from X? How much amount of deviance do I see from Y from its uh, mean? And I divide it by the standard deviation of each of these independent random variables. Okay. All right. So let's go to, that wasn't like an aside. And we'll keep doing asides for each of the problems that we talk about. Okay. So let's take problem B. Problem B asks us to examine the plot, and there appears to be a car with 100 horsepower, which has a q-sec of 23. So this is this point here. Now, if this q-sec were to be reduced to 20, so if I were to delete this point and add a new point at the same value, but I added somewhere here. Okay, so this is 20. This is 100, 20. Okay, 100 is the x, 20 is the y. If I were to add this new value, what do you think would happen to the correlation coefficient? Okay. All right. Anyone wants to take a guess as to what would happen if I were to remove this point and add a new value here? Okay, increase in magnitude, right? That's great. So everyone sees why. So this particular value of this particular data point is in some sense an outlier. Okay. One thing that you notice is a lot of data points are clustered around this particular area. Okay. So if I add this new point here, this will essentially end up increasing my correlation coefficient, because in some sense, the outlier was kind of reducing it, because given that this point is outlier, it's difficult for me to really predict this point from any of the SX value, because all the other points are exist in a cluster. And hence, if this particular point, the red point here, was to be removed and made a blue point, then this would again become a part of the cluster, which is easier for me to predict. And hence, you'll see increase in magnitude. Okay, increase in magnitude of the correlation coefficient. Now, this magnitude is essentially given by absolute value of R. Okay, and hence I was clear about making this magnitude, because there is a negative correlation, right? So let's say if the original value with the, so let me write that in red. So if we have the outlier point, if the original value was, let's say, minus 0.9, then with the blue point included, it will be minus 0.95. Okay. So the actual value has reduced, but the total magnitude has increased. Okay. And hence magnitude is important. Okay. Now let's move to problem C. Problem C talks about giving you access to how much amount of deviation do we see from X and Y jointly, the standard deviation of X and the standard deviation of Y. And you're asked to calculate the correlation coefficient. So the correlation coefficient, again, intuitively, what is it capturing? It's capturing how much amount of uh, X or Y can be predicted from the other variables. So how much amount of X can be predicted from Y, or how much amount of Y can be predicted from X. So this formula is, again, very simple. You look at, so the top term in some sense, so the top term is actually called covariance. This is your covariance. And if you divide it by their corresponding standard deviation, then it becomes correlation. Okay. So this covariance term, which is the numerator, is essentially capturing how much amount of variation do you see jointly between X and Y. Okay. And then you adjust it for the fact that how much amount of variation exists in X and how much amount of variation exists in Y. This value, if you plug in the numbers, I think comes around minus 0.707. Okay. And you can see why the sign is negative, because this particular term has negative sign. Okay. Whereas Sx and Sy will always be positive. Okay. All right. Move to part D. Now we're asked that to test if the correlation coefficient is significant or not. So in order to test whether this correlation coefficient is significant or not, so at this point, we have only found out what the value of the correlation coefficient is. Okay. Now the significance that gets attached to, so I'll write this here. What does it mean to be significance? So significance of R. So when you're interested in identifying whether the correlation coefficient that you've actually found, is it significant or not, what does it really mean? So in some sense, it means that the value that you're obtaining here, do you have enough statistical significance to assign it the value that you're assigning in some sense? Okay. So let's see what that really means. Let me first talk about what the statistic is. So this is known to follow a t distribution. And this t distribution is essentially dependent on the value of the correlation coefficient. The next thing that it requires is the number of samples that you have and the R square value. Okay. And one quick thing that you can notice from this formula is if you increase the number of points, then your t statistic is going to be higher. Okay. So let me make this clear. So if you increase the number of points, then your t statistic is going to be higher. Okay. That's kind of going to be your case of testing for t statistic. The degrees of freedom are given by this number here, n minus 2. So essentially, you will calculate the t statistic for this R. The reason we are calling it, the reason this is a t distribution is because R in some sense follows the assumptions of normality. Okay, so if you do this for different sample sizes and plot the distribution of R, it will appear to be a normal curve, and hence it's expected to follow a T distribution. Okay. So given the particular T statistic and the degrees of freedom, we can find out whether the correlation coefficient is significant or not. So we go to table 4 and look up this particular value. Okay, so table 4, here degrees of freedom is around 30. So this is the row that we are going to look for. And we did not actually calculate the T statistic. So let's first do that. So the T statistic following this formula, if you calculate, will be minus 5.475. Okay. So again, just what is it that, why are we interested in the significance of this? So sometimes it could happen that you're able to find out a correlation coefficient, but since there is a lot of variability in the data, or if you have lesser number of data points, that correlation coefficient might not necessarily be significant. Okay. Attaching it as significance essentially tells you, in some sense, the confidence of the R being true. Okay. So if you have, so let's take a extreme example. Let's take this example where you have few data points. Okay, you just have 5 data points. And you also have these data points. Okay. In this case, as you can see, seems to be a positive correlation, but it's likely that the significance that you get out of this p-value, so the T statistic might be low. So R is high and T statistic might be low. And that's essentially just arising because there's a lot of variability in this kind of data. Okay, and that's why we are interested in also not only calculating what the value of R is, but in some sense how confident we are of that particular value. Okay, I mean, let me correct that. So it's not about how confident you are. It's essentially explaining what is the probability of seeing something as extreme as what you are seeing, having adjusted for the fact that you're going to randomly sample for a certain number of iterations. Okay, exactly the interpretation of what your p-value interpretation is. All right, so if you look up this particular value on table 4, so we were at degrees of freedom equal to 30, and we start looking for 5 again. So it's a negative value, but we are in the positive domain. So on this row, this value highest is 3.646. So our P definitely is going to be less than 0.005. Okay. All right, so your P is less than 0.005, and hence we reject the null of, so I did not specify the null, but the null was that this correlation is essentially 0. Okay. Any questions? This is actually a correction. So I'm looking for a two-sided version. So I need to multiply this by 2. Okay. Because I implicitly assumed that my alternate was R not equal to 0. Okay. Depending on what your null is. In this case, I assume that null is not equal to 0, but I did not explicitly clarify it. But if this is my null, then I need to multiply this by 2. Okay. All right, so we'll move to part E. And part E asks us this question, that the car manufacturers are now interested in whether manipulating the horsepower can alter the QSEC. Okay. So from the analysis that you've done so far, do you think that's a good idea, or do you think that's not a good idea? So should the car manufacturer just manipulate the horsepower of the engine in order to manipulate the QSEC? Is that something that you would advise, or is that something that you would not advise? Why or why not? Anyone wants to take a hit at this problem? So what is it that we are interested in? We are interested in the car manufacturer. They are interested in if they can manipulate the horsepower so that they can alter the QSEC. Okay. So imagine you're a car manufacturer and you want to essentially get certain value of QSEC. The way you're going to achieve is now you know the correlation. So you'll say that, okay, let's manufacture a car of uh, 300 horsepower. Okay, this point here, so that I can achieve a QSEC of, let's say, this will be around 14. Do you think that's a good idea or no? So you want to achieve a certain level of QSEC, and the way the car manufacturer wants to do this is by manipulating the horsepower. Is that a good idea? Okay, and why is that? So why is that not a good idea?
Is it because this is just talking about correlation, but you can't infer causation?
Great. Yeah, that's perfect. Okay, so correlation does not imply causation. That's something you would have heard so far in a lot of your classes. So correlation does not imply causation, right? So if I want to manufacture something which has a certain QSEC, I should not rely on manipulating the horsepower. Okay, the car manufacturer should really think about other factors that really go behind behind the value that determines what your QSEC should be. So sure, there is a correlation between horsepower and QSEC, but it cannot be used for predicting what the value of. It cannot be used as a causation to find out what the value would be. Okay, so it's not a good idea. So we only know that HP and QSEC are correlated. So this does not imply that manipulating one will necessarily manipulate other. So manipulating HP would manipulate, would change QSEC, okay, or vice versa. Okay. Okay, so that was about correlation. Okay, so it's a very simple concept. You are given two numeric variables, you figure out whether they are related or not by calculating this particular number. Okay. Now we go into a slightly advanced version of it. And the way we do that is we will look at something called regression. Okay. So the idea behind regression is very simple. So you're given, again, two variables, x and y. So x and y are numeric. And again, I want to be able to predict y from x. Okay. So imagine you have certain distribution of data points like this. And the simplest way you can think about doing this, right? So we always start with the simplest possible model. Okay. And this is one simple model of, so let me make this a bit more clearer because I want to contrast it as to why we are doing this. So imagine you have these points. Okay. And so you can think of multiple ways to actually uh, fit this value, right? So one way I could think of is to fit a curve which would look like this. But if you think about it, this curve is like a complicated curve that you want to fit, right? It's a complicated model because it's changing at a lot of points and its curvature is changing and its values that it traverses is completely dependent on, is changing a lot, right? So that's not like a good idea. You would like to start off with a very simple model. And the simplest model that we can think of is almost always linear. Okay, so I can make this line pass through uh, somewhere in between the points, right? Uh, the reason this line is limiting in some sense is because there's no way I can make them pass through all the points. So I say that I will accept this line as a good model if it minimizes. So let me get rid of this. So I'll say that this particular line is a good fit for predicting x from y, and I impose a condition as to how should I fit this line, right? So why did I only fit this line, and why did not I pick up a line which would look, let's say, look something like this? Okay, why just that line? So there's one more assumption in that goes in basically being able to fit that line. And what that assumption is that the residuals that you see, right? So this is a line, so the line of fit or regression line. Sorry, there's a lot of red points still remaining. So the other assumption that I'm posing on this line is you minimize the residuals. Okay. So the residual is essentially given by how much amount of difference do I see in the value of y. Okay. So what really is happening? So let's take this particular point. Okay. At this particular point, my x value is fit. So this is what my x value is. Okay. So this is what you're observing. However, what you're fitting is this. Let me. Okay. So this is okay. So notice that you're essentially saying that y varies based on x. So the thing that the y is the dependent and x is the independent variable, right? So x varies on x-axis, and I'm trying to predict what the value of the y is. So the thing that I'm actually observing at this value of x is this observed value. However, I'm not able to fit it exactly. So the value that I'm really going to predict is on the y-axis is this value. Okay. So in some sense, I'm creating an error. I'm doing an error, and that error can be quantified by this is your residual. Okay. So that's called the residual. And the way I'm going to fit this line is I'm going to say that I want to want to fit a line so that this particular residual term is minimized across all the points. Okay. That's the basic gist of how you fit a line. Okay. In some sense, you can think of this that in the sense that I'm allowed to make certain amount of error in being able to predict y at the cost of fitting the most simplest model which passes through all these points. Okay. And that's essentially what so this is essentially in all respect, this is your regression summary. Any questions about regression, anything that's not clear? Okay, I gave you a very broad overview of what is it that you're really doing. We'll go into the math part of it step by step, but is the understanding of residual clear and the regression? Any questions? So this is residual and this is residual as well. This is residual as well. Okay. Now, one recurrent question that you'll see in your project, or I mean, it's not a recurrent question in your project, but one recurrent question that you'll see for the next part of your either exams or your homeworks is amount of variance explained. Okay. So notice, let me redraw the figure. We'll talk about the discussion problem in a bit, but I want to first clarify this problem. So you have y values somewhere here, here, and here. Okay. So these values, that essentially means that there is some variance in y. Okay. Why is there variance in y? Well, because these values are not exactly all equal. They are varying. They're varying, right? So if the variance was supposed to be 0, then all these 5 points would have collapsed into 1 point. So there is some variance in y. There is also some variance in x. Okay. Why is there a variance in x? Well, because these are plotted at different values of x, and hence there is variance coming because of x. Now I will fit a line here. So this is my best fit line. This is my best fit line. Okay. And now for each of these values of x, let me use a different color. So for each of these values of x, I can now predict the value of y. Okay, it's not going to be exactly the same as what I observe, but it's going to be close enough. Okay, similarly for this value. Okay, so obviously your predicted points will always lie on this line. Okay, because that's essentially what your model is. So now your predicted points happen to be lying along this lines. Okay, so this is point number one. So let me give this number one, two. Let me give this numbers. This is x1, x2, x3, x4, and x5. And I'll call the predicted points with a hat. So this is y1 hat, y2 hat, y3 hat, y4 hat, and y5 hat. Okay. So earlier you were observing variance in the values of y. Again, these you'll also obtain another sort of variance, which is coming from these 5 points, right? So this is your variance in y hat. Okay, y hat, just to be clear, is predicted from the best fit line. So one thing that we can now do is we can ask how good of a model is my blue line, right? So how good is the blue line? Okay, and one way to answer that question is, is my model, is my blue line able to explain all the variance that exists in y, right? So in some sense, if variance in y hat is kind of equal to variance in y, right? Then this is a perfect model. It's a good model. So if the variance that I see in these y points is exactly equal to the variance in y, then it's a very good model. And you can see why. Okay, so you can see that if I were to let me do this in here. If we had, in an alternate world, if we had still had these x1, x2, x3, x4, and x5, and all my points were perfectly aligned. Okay, my line, that means, would pass perfectly along all those points. Okay, in this case, your variance in y hat is exactly equal to your variance in y. Okay, so in some sense, if you're essentially able to reduce the extra amount of variance that's coming because of your residuals. So if your residual is equal to 0, okay, then you'll get a perfect line, and that will be the variance explained. Okay, so the variance explained is, in summary, equal to r square. Okay, this is essentially equal to square of your correlation coefficient. It's also equal to, so let me first write down what is it exactly equal to. So I want to explain, so this is percentage of variance explained. I want to explain the amount of variance that I see in my y values. And the way I'm going to see that is, I'll first look at the variance of, sorry, this is my square. I'll look at the variances of, um, so let me write this in a reduced format because that's easier to explain. So I want to be able to calculate how much amount of variance is explained by my model by the linear fit line. And that's essentially equal to 1 minus how much amount of variance is being explained by the residual. Okay. Now the reason this is coming into picture is because my line is not a perfect fit. It does not pass through all the points perfectly. So at each point, I'm carrying out certain residual. There's a residual here, there's a residual here, there's a residual here, and there's a residual here. So I'm asking how much amount of variance that I see in Y can actually be explained by by my model. And that's essentially equal to 1 minus how much amount of variance do you see in the residuals divided by how much amount of variance do you have in your R, right? So this is Sy is equal to Sy square minus Se square. So intuitively, what am I doing? I'm essentially accounting for how much amount of variance do I see in Y that's coming because of the residuals, okay, on the numerator. And you can see in this particular case, and when you're all the lines, when the line passes through all the points perfectly, this percent variance will be equal to 1, right? Or 100%, however you want to call it. Okay, because all the variance that exists in the Y can actually be captured by my line. The line can perfectly predict how much amount of variance you have in Y, again, because it's a perfect fit, which is not the case that's happening in this example. In this example, I recur a certain amount of residual, which is not something that's able to capture my variance. Okay, any questions about this? Does everyone now understand what the variance explained thing captures? So this is the formula for carrying this thing, but there's a shortcut. If you calculated the correlation coefficient, this is also equal to R square. Okay, any questions? All right, so if not, I'll proceed and we'll solve problem A. So you're asked to calculate the correlation coefficient, which is again very simple. You're essentially given all the ingredients for calculating this. And if you plug in the numbers, this comes around to be 0.98. Okay, in part B, we are asked this question: what proportion of the variance in sun's height is explained by the linear regression of sun's height on father's height? And what does this really mean? So how would you plot this data, right? So in order to plot this, I will plot my father's height here, okay? And why am I doing it here? Because this is my independent variable, right? You're using father's height to predict the sun's height. So this is going to be your Y variable, okay? So again, we have kind of fitted a line here, and we are asking how much amount of proportion of the variance in sun's height. So this is your variance can be explained by the variation by the linear regression of sun's height on the father's height. So when you see this term, linear regression of sun's height on father's height, that almost always means linear regression of Y on X. Okay, so this is your Y variable, and this is your X variable. So it's essentially asking if you fit a line, how much amount of variance can be explained by this line. Okay, and now you know how do you do that. So you're given Sy square, you're given Sx, you're given Sy, and you're also given Se. So this is how we will calculate. Okay, and if you plug in the numbers, this will come out to be 0.96. 0.96 also happens to be 0.98 square, which is your correlation in part A. Okay, so there are two ways to calculate it. This one is slightly quicker because you've already calculated the correlation coefficient. But if you're given the standard deviation of the variance in Y and the variance of the residuals, then you can also calculate it using this formula. Okay, so it's essentially square of part A. Okay, calculate the 95% confidence interval for the slope beta 1. What is beta 1? So when I fit this line, the way I fit this is I said that Y is equal to beta naught plus beta 1 X. Okay, this is your intercept, and this is your slope. Okay, now what does an intercept look like? So I'll have to draw another diagram, but let me draw it here. So this is beta naught, and the slope essentially is this this slope here. Okay, so this is slope of this line. Okay, so slope of 0 would, so this is beta 1 equal to 0, flat line. A slope of beta 1 equal to 1 is 45 degrees. Okay, and similarly you can extrapolate. Okay, all right, so how do we do this? So how do we calculate beta 1's confidence interval? So first of all, we need to calculate what beta 1 is, right? And the beta 1, intuitively you can understand that you're predicting the deviation of the relation of y on x. So in some sense, it's essentially dependent on how much amount of variance do you see in y. But at the same time, it also accounts for how much amount of variance you see in x. So this is the formula. You'll have access to it, but intuitively, you're essentially able to explain how much amount of variance you're seeing in y, having adjusted for how much amount of variance you see in x. Okay. All right. So if you plug in the numbers, this value comes around to be 0.45. But we are asked the confidence interval. So we need another factor, another value from this, which is the standard error. Okay. And the standard error for this coefficient, again, you'll need to have access to these formulas. It's given by standard error of the residuals divided by standard error of the standard deviation of x times square root of n minus y. Okay, this is the term that's coming because of the standard error. You guess get value will be 0.032. Next, probably run out of space here, but let's see. So this is beta 1 plus minus t 0.025 and standard of beta 1. Okay, this is your CI. You also need a value of t 0.025, which if you go back to your table, this can calculate 2.306. The degrees of freedom for this are given by n minus 2, which is 8. Okay, you can verify this particular value by looking at the table. Okay, and then what you have to do essentially is plug in the numbers here. So beta 1. Okay, so one thing again, everything that you learned about confidence interval applies here as well, right? So the beta 1, this interval does not contain 0. And hence, this coefficient that you're calculating is essentially significant. Okay. So if you do this in R, you get a p-value. That p-value essentially explains that what's the statistical significance associated with either the intercept or the slope. Okay. So this does not contain 0. Okay. That's something that you just need to be aware of. Okay, I'll move on to this problem. It's an important problem from the point of view of your project. Okay. So it's a very simple problem. All you have to do is interpret the residual plots. So on each of these figures, A, B, and C, on the A part, you're given the regression of x or y on x. Next figure is the residuals plotted against the x values. Okay. And you're asked for each of these scatter diagrams, can you explain how do you get certain, why do you get those residuals? Okay. So, okay, what do you think about residuals on plot A? Do they look normal? Is there a pattern? No pattern? So I'm talking about this one. Maybe I should enhance it. Okay. What about residuals in part A? Are they normal? Are they random? Are they? So what should be pattern, right? So one thing that I forgot to mention earlier was the way you're fitting this normal, you assume that the error, okay, so we'll probably add it here. So the residuals are assumed to be normally distributed. Okay, and with that, I'll also like to point out that if you do this regression on count values, if your x is count and your y is count, that means it's discrete data, then this assumption of the normal distribution of the residuals being normally distributed actually does not apply, right? So the way we do this linear regression as to what we are studying in the class is not the best model for counts data. Counts data essentially is discrete data where your x and y both are discrete. But for practical purposes in the class, you can use this model. But if you have both x and y accounts, then there are other models which are used to fit x and y. You still fit a line, but the assumptions that go behind this residuals are in some sense relaxed. Okay. Right now, your assumptions are these residuals are normally distributed. Okay. So if you plot them, if you plot these residuals on the x-axis along with the x values, you expect to see a normal or distributed pattern. Sorry, you expect to see a random pattern. Okay, so the residuals here are normally distributed. Okay, so this implies that the linear model is sufficient to explain the relationship between x and y. Okay, let's take part B. What do people think in part B? You see like an umbrella or a U pattern in the residuals. What do you think is happening? Yes, the residuals depend on X. Great. Any other observations? Anything else that you can add up to that? So if you see a pattern which looks like this, then it generally means that the residuals definitely depend on X. And in this case, because there is a U pattern, this generally implies that you require a higher order fit. What does that mean? That a linear model is not sufficient. You would want to fit like a curve. Okay, a curve means something like a quadratic curve. Okay, that means so I just had linear model has beta O plus beta 1 x. You wouldn't want something like beta 1 plus beta 1 x plus beta 2 x squared. Okay, for this term. Okay, final one, which you have probably some of you would have already seen this in your data. What is happening? So residual is low at lower values of x, and it seems to go higher at higher values of x. Okay, so in fact, in some sense, there is some sort of a linear trend in the residuals that you're seeing. Okay, and you might see this in your data when you do the plot, for your own data set. Okay, so this essentially means that there are the two ways to interpret this is first of all, residuals depend on x, and so higher x implies higher residual. Okay, which essentially means that maybe there is some other confounding variable which you can adjust for. Okay, so there's some other confounding variable which if you adjust for, if you add it. So what do I mean by that? So you have y equal to beta naught plus beta 1 x, but probably there is y equal to beta naught plus beta 1 x plus some other beta 2 z. Okay, in our class we just restrict ourselves to this model, but there may be some other variable which if we account for, this pattern will go away. Okay, and it also means that the variance of x is this is 1, this is 2. So the variance that you see in your values of x, it's not essentially constant. So there is a lot of variance happening at higher values of x. Okay, that's kind of a hand wavy interpretation of what is really happening. But if you probably adjust for other confounding variables, you might be able to get rid of this increasing pattern. Okay, all right, that is it. We're almost out of time. Any questions? Any questions about the project? Any questions about uh, the handout? I also realize this is probably the last handout we are going to discuss. We might not have a handout for the next week, but I'll let you know in advance if that's going to be the case. Okay, this is kind of the final week. So I think Peter is going to talk about some new stuff which will not be on the exam. So if that happens, I'll probably just talk about some examples, or we might just review the entire class that we have done so far. Okay. My office hours hold as such, so if you have any questions, feel free to ask me or email me if you want to set up a different time to talk about. Okay. Make sure you turn in your projects on time. We don't want it to overlap with your exam week or study week, and hence it's due on the last day of the classes. Okay. So make sure you turn it on time. We'll not be able to extend the deadline. Okay. All right, that's it from my side. I'll stick around for a couple of minutes if there are any questions. You can, you're free to leave.